All right, hello everyone. Welcome to the second week of PChem 2. We have finally gotten past our Maxwell-Boltzmann this, that, and we are on to something much, much worse. Anyway, today's lecture, we're gonna take one more week warm up until we get to quantum. When we get to quantum next week, we're going to spend basically the rest of the semester on that. There's an example problem that we're going to analyze this week that is really just part of your general education, has to do with more Boltzmann Equation, this, that, and is a good warm-up for quantum. We're going to do some problems that are very quantum mechanical-like, but are not quantum mechanical. At times the equations will stretch across the board, but the thing is that the phenomenon we're studying, which is we're basically going to learn how a light bulb works, you have some intuitive sense about that. You probably have a pretty good idea how a light bulb works without me having to tell you anything. That's great. The hard part will be developing on the mathematics. When we get to quantum, the exact opposite will be true. The first month, the mathematics are actually going to be really easy, but the interpretation is going to be difficult. Like how to think properly about it. Towards the end of the semester, then we're going to be doing a little bit of both. The quantum mechanics, when we get to like the quantum mechanics of the hydrogen atom, we'll get back to those equations stretching across the board, but by then you're going to be quite used to it, so no problem there. Let's see. I did get some feedback and some email from some of you, and I wanted to share that. Let's see. Ladiesman227 writes, more chickens. More chickens. Well, all right, more chickens it is. And I don't have any other emails, so with that, why don't we go ahead and get started on today's lecture, which, again, we're talking about the light bulb, but of course, light bulbs are photon machines, and photons are waves, and so it was understood for the longest time. You may recall that there is a famous painting of Isaac Newton. It's probably in a lot of your middle school science textbooks of Isaac Newton holding up a prism, a glass prism, and of course white light comes through the window and out comes red light. Obviously this is Dark Side of the Moon from Pink Floyd. Green and blue. The blue light gets bent a little bit more. By the way, that's why the sky is blue. Blue light is diffracted more than red light. And our atmosphere is basically a giant prism, that's why the sky is blue. You can understand this behavior from basic physics. You've had that before, so I don't think we really need to go over it. Light is a wave. You can think of it as like waves over the ocean. It goes on forever, right? Which has a problem with the concept photons as particles. You may have heard the term particle-wave duality as it applies to quantum mechanics, and that also applies to photons. And a lot of this comes about from Einstein 1905. That actually should be written down. 1905, one of Einstein's E-I-N. Yes, you saw me misspell Einstein, but I'll fix that in editing. Einstein in 1905 was able to describe the photoelectric effect, where he described light as particles, which was very controversial and took a long time for people to accept. Part of your general education, now we're not here to talk about the photoelectric effect, but as part of your general education, you should know something about this. And it has to do with the fact that, Einstein came along in the right time. In the early 1900s is when electricity became generally available to people, like in your house and whatnot. And there was also an explosion of scientific progress made at that time. There was two reasons for that. One, it turns out that a ton of new elements were discovered about that time because you have to use electrolysis to isolate those elements. Many elements can only be isolated using electricity, so when people had electricity, they isolated elements. Cool. Number two, vacuum chambers. You need electricity to run a vacuum pump to get a vacuum chamber, and what you can do with that is take a piece of silicon, any semiconductor, let's just make it silicon because you're familiar with silicon. Okay, and what you're going to do is you're going to put that in a vacuum chamber. And we all know that it has electrons. What you do is you shine light on it. Now, if you want to get used to a wavy line with an arrow, and I always write little h nu, Planck's constant times frequency, which is energy, that's a sign that that symbol means I'm shining light on it. You should, hopefully you've seen that before, and if not, there it is. And what happens is electrons come just shooting off the silicon. Obviously, you need to keep that in a vacuum because the electrons will run into something otherwise. And then above it is some kind of detector that can see that, sure enough, electrons are coming off the silicon. Okay, so what about that? That's not particularly hard to understand. Here's the thing that really slayed people back in the day. Imagine I have two lamps, a red lamp and a blue lamp, and I put my hands underneath them. Ouch, right? Look, these are intense lamps, right? You know, like red lamps when you see people, you know, keeping food warm. You can imagine a blue light is just as intense, and if you put your hands underneath them, they get hot, and maybe, you know, some lamps, within really a few seconds, you're like, ooh, that hurts. Because energy, of course, is being absorbed by your hands. Ergo, red light or blue light, doesn't matter. Light is energy. It's quite obvious. It was to them back even in the day. But these photoelectrons, that's the word for them, photoelectrons, are only observed with blue light and not red light, specifically around infrared light. In other words, there was a threshold for wavelength. You had to get from the infrared, when you shine infrared light on a piece of silicon, nothing happens, and then when you get to the visible, all of a sudden electrons start pouring out. But why is that? Energy is energy, and a wave is like a ripple across the ocean. Einstein figured out that these things are more like particles. So what I'm going to do here is, tell you what, let me redraw that, I don't like that. I am going to show you Einstein's explanation, which is going to, again, be kind of obvious, but then I'll get into more detail. And what I'm going to do here, something you have to get used to, is actually I'm going to draw two things at once. So this is the silicon. So I'm drawing just a slab of silicon, so it's like a stupid picture. But I'm going to overlay that with an energy diagram. So I'm going to say the y direction is energy. And I'm going to say that there's some like level, energy level, which is where the electrons reside. So the electrons inside of the silicon have a certain energy level. Now that's because, you know, electrons, they don't like being right next to each other. That's bad. But the nuclei, the silicon nuclei, are something the electrons like. So electrons would prefer to stay in the silicon chip. Of course you know that because it's not like you pick up a piece of silicon and the electrons fall out, do they? What if they did? Okay, here's how that works. Okay, so it turns out that basically there's some energy level, let's call that right here, which is called the vacuum. And if I'm getting all technical, this level right here is called, sorry I don't like the diagram, I should have thought of this ahead of time. So this is the vacuum energy, which I'm drawing on top of the chip of silicon, and this we'll call the valence. I'm using some specific terminology for solid state physics, but you don't have to worry about that. I just want to make sure I'm using the right words, irregardless. Okay, so here's what happens. The vacuum, I know you know what a vacuum is, it's the absence of air, but it actually has another meaning when it comes to the photoelectric effect, which is that the vacuum energy is the energy of an electron in a vacuum all by itself. And that's just some energy. We can actually call it zero if we feel like, it doesn't matter. And relative to that is the valence energy, and that's, and the electrons are happy to be in the silicon. Okay, so what happens is along comes a photon, and it kicks out the electron with a certain amount of energy that's greater than the vacuum energy, so the electron can get kicked out. Yeah, notice that I gave it a little bit of excess, more energy than the vacuum energy, and that gets used as kinetic energy. so that excess energy is conserved, right? So this electron can escape the silicon, and it moves off with some extra energy that gets it moving, which our detector can interpret. It's actually surprisingly easy to build devices that work this way. Now you can imagine that if you have higher frequency light, or really, and that will pop off the electron with more kinetic energy because that light is higher energy. In higher energy, higher frequency still, that electron gets popped off with even more kinetic energy. So this is increasing kinetic energy. So kinetic energy is going up as the frequency of light increases or the wavelength decreases, because that means the photon has more and more energy. Okay, so this is the photoelectric effect. And I'm writing that down now because I forgot to write it down before. And there's not much to it, right? I think that's relatively easy to understand. But now here's the part that won Einstein the Nobel Prize. The thing is that these electrons have to have energy from the photons, which again is not hard to understand, but electrons also have momentum. Now, you've probably had enough physics, and maybe this was brought up maybe in freshman chemistry as well, that there are fundamental conservation laws. All processes conserve mass, conserve energy, and conserve momentum as well, right? Maybe you even had that in high school physics. Momentum is conserved in any interaction. Well, the damnedest thing is, that means that for this to work, the energy is conserved, and you can see how that is, but so is momentum. So therefore, photons have momentum for a singular anyway. So for photons to have momentum, they have to be more like particles, right? Like a marble, one marble hitting another. And that analogy is crude, but that's exactly what's going on. And the only way for that to be true is that if light is not like a continuous wave that goes across the ocean, it's like a single particle. Now, it's a wave because of Pink Floyd, but it's a particle because of the photoelectric effect, and it's both simultaneously. You might think like, oh, okay, well, what experiment shows which one is it really? It's really both at the same time, and that is something that's very hard for people to wrap their heads around, but this is how it is. Let me preview quantum mechanics. When we cover quantum mechanics, we're going to say the same thing about particles with mass, electron, protons, neutrons. We're going to say that they're just like photons. Anyway, preview, but we're not there yet. Okay. One last bit about this, again, for your general education. What's kind of neat about this is that you can figure out Planck's constant from this. Now, as before, I mentioned that whenever I write down like a photon, I'll draw a little wave with a circle, and I usually put a little h nu. H nu is, I'm praying you've seen that before, Planck's constant times the frequency of light is the energy of a photon. So let me write that down. The energy is Planck's constant times the frequency. The reason I'm writing that down is that actually I usually prefer to do this. Speed of light over the wavelength of light is the frequency. I tend to use this one more than I use that one, so I want you to see that. Another neat thing is about Planck's constant, where we know what that number is from the photoelectric effect. Here, let me show you what happens is we can do this kinetic energy, measure the kinetic energy, and I'm telling you, it's not hard to design an apparatus that does that. And if you do that as a function of the energy of light, and again, let me use my wavelength form, what you find is that at infrared wavelengths, as you go closer and closer to the visible wavelength, there's no kinetic energy because there's no electrons. And then, bam, it just kicks in. All of a sudden you see electrons and their kinetic energy increases, as you go to higher frequency or shorter wavelengths. And guess what the slope is? Right, the slope is proportional to Planck's constant. And so that's how we know what Planck's constant is. I just thought that was kind of neat. So anyway, I guess that's all I have to say about that. This was just a warm-up just for your general education about particle-wave duality, because that's really what quantum mechanics is about. I can't resist. So what really happens, again, I'm previewing what I'm going to tell you about next week, was this guy De Broglie looked at how Einstein described what was thought of as a wave, as a particle, and De Broglie says, well, what if particles were waves? And that's where you get quantum mechanics. Anyway, I shouldn't be telling you that, but I can't resist. Anyway. All right, so what are we really here to talk about? What are we going to spend the week on? We are going to spend the week on what is called the black body. Wait 1 second. Am I using the right? Yeah, I'm using the right board. There's two boards here. I got to use the right one. Black body radiator. And this is the stupidest name ever come up with for a light bulb. This is really a description of light bulbs, but for reasons of being perfectly exact in our descriptions, the term black body radiator is used. Now, the reason that is what I'm really describing here is a box. It's perfectly black and it's hot. Now, you know that hot things emit light. If it's not too hot, it'll emit red light. As it gets hotter, it turns white. And if something is really hot, it emits blue light. Okay, so this is a black metal object that's hot. So there's photons. There's photons inside of it. Let's make the heat inside. So, okay, so photons are inside of it. Okay, whoop-de-doo, so what? It's a black body because what has to happen is that when some of the light inside is created by virtue of heat, it travels through the box, hits the wall, and is reabsorbed. Why is that important? It's important because it means that it maintains equilibrium. It maintains its temperature. And if it creates light, it has to reabsorb it, or that it wouldn't happen. It would not maintain its temperature. Whatever, man, it doesn't matter. It's a light bulb, right? A light bulb does require a constant input of energy via current because it sheds so much energy in the form of light and heat. But whatever, it doesn't really matter. What I'm describing today is a perfectly good description of a hot metal box. That's exactly what it is, or a light bulb. Anyway, but I am obliged to describe what exactly is going on. Now, in terms of the model problem, the way that this works is you have a hole in the box, a really small hole, and you occasionally let light come out, and you have a spectrometer. Now, the way you do this in science is you draw an eye for your spectrometer. You see this in publications. It's kind of creepy, and I didn't do such a good job drawing it. But anyway, so the eye, of course, will report the spectrum, and the spectrum looks something like this. And whether you actually build, so there are companies that actually build these things for like calibration purposes, because a light bulb is not exactly right in terms of like the intensity versus wavelength, which looks like this. Actually looks just like our Maxwell-Boltzmann thing, doesn't it? And it's related, but anyway. So again, if I put a spectrometer to a light bulb, this is what I would see. Where the peak here is the only thing to note about the spectrum of a light bulb is that the peak is a function of temperature. The wavelength at the peak, I should say. So what you find is that if this black body or light bulb is at 1,000 K, it would appear red. If it is at 5,000 K, the object would appear white. White hot, right? Sometimes you get like a hot poker in the fireplace that hot. That's pretty hot though, that's kind of nuts. If you're at 1,200 degrees K, the object would appear blue at that. But reality is most things melt long before you get to 1,200 K. In fact, the reason that we make those old typey, old incandescent light bulbs out of tungsten, tungsten is one of the few metals that can go to 5,000 K and not melt. Iron won't do it. Iron will melt. Actually, it's like melts at like 1,000 K. Anyway, that's why we make light bulbs out of tungsten. Oh, and guess what? The 5,000 K light bulb, that's what our eye tells us about the black body radiator at 5,000 K, or a light bulb that's at 5,000 K. But there's another thing you can point the eye at and see the same spectrum, the same 5,000 K spectrum. It's the sun. Now, have you ever wondered where, like, astronomers say like, oh, the surface of the sun is at 5,000 K? You know how they know that? It's because we can calibrate a black body, get its spectrum, and it's a perfect match for the sun, so long as the black body's at 5,000 K. Therefore, the sun's surface is at 5,000 K. I guess it's hotter on the inside, but anyway. That's how they know these things, by the way. I thought that was kind of neat. And also, those new LED light bulbs, which from my perspective are relatively new. I don't know if you've noticed, but the box actually describes them using colors, using temperatures. It's a warm temperature, it's a cool temperature. And that's because of the way black body objects, the perceived color is dependent on temperature. Anyway, that's where that comes from. Okay, so our job is to derive why a light bulb spectrum appears the way it does. Now, the black body box is L by L by L, but tell you what, like I say, I happen to know for a fact that regular incandescent lamps look exactly the same, with just some very minor differences. So we'll say that the light bulb is L long in our mathematical description of the light bulb. Okay. This week's lecture comes in 2 steps. The first step we're doing today is rather easy. We're going to apply the Boltzmann equation to a light bulb. And then the next step I'll explain towards the end of lecture. It's a little bit more difficult and it will take 2 days. So that's Wednesday and Friday's lecture. Today's lecture is to talk about the energy of a light bulb, energy of photons, and to use the Boltzmann equation to describe that. Of course, you still remember that the Boltzmann equation is the probability distribution by which nature doles out energy. And you can see where temperature comes into effect, kBT, so if something is hot, it is blue colored. If it is not so hot, it is red colored. We assume, of course, an object that's at room temperature or cooler is not emitting light at all, but we won't consider that. Okay, so we're going to input the energy of a photon. And this is where I have to make a little bit of, I have to slow down already a little bit. Remember my analogy talking about, you can imagine that when you go to a deli and they have a lamp keeping food warm and it's kind of red. And if you put your hand underneath there, you probably wouldn't want to do that for too long, maybe a few seconds, it would hurt. But if you had a blue one, it would do that too. Now why does that mean? It would feel the same. And that's why people were confused at first about the photoelectric effect. They're like, why doesn't red light do something? It should do something. It's still energy. And for all the reasons I just described, because there's a finite energy between the valence energy and the vacuum energy, and you have to cross that threshold. Okay, whatever. Energy is still energy. Photons still have energy. And yes, red photons the individual photon has less energy. So why is it that I can perceive, if I have my 2 lamps and I'm putting my hands underneath them, why would I get burned just as bad by both? Well, it'd be a little bit of engineering. And again, this is an aside. Maybe you don't even need to write this down. But if I was to have 2 lamps, give both my hands enough energy such that at the same time I was to go, ouch, that hurt, the way you do that is the blue frequency is greater than the red frequency. So it seems like the blue land is going to be more umph, it's going to have more umph and hurt me more than the red. But the way you get around it is you got to remember that there's a certain number of red photons, right? And there's a certain number of blue. So the way that you would make both these intensities equal is if the number of red photons is greater than the number of blue. So more red photons accounts for the fact that it has a lower frequency, and thus each individual photon has lower energy. Again, you just compensate that by having more red photons. Okay, again, hopefully that's like, if you're thinking like, well, gee, that's like middle school obvious. Yes, but now here's where I'm going to use that. I'm going to use that fact in the Boltzmann equation for energy. Now, think about this. So here, let me write that down. So energy of light is not just Planck's constant times the frequency, it's the number of photons times Planck's constant times the frequency. Now, why is this important? Think back to when we did this just 2 weeks ago, and I put in for energy 1/2 mv squared. Now, it's energy, but I don't see the letter E anymore, I see V, velocity. And I did a lot of manipulation with velocity. I solved for the normalizer by integrating a function of velocity. I then took the result and calculated average velocity, yada, yada, yada. But of course, that's really, I can relate that to average energy. So what am I doing here? We're not going to mess with the Planck's constant because it's a constant. I could do all that stuff, like figure out the normalizer based on the frequency. That's normally what I want to do, but that's actually the wrong thing to do. We're going to keep the frequency, or here, let me go back to my wavelength. We're going to keep the wavelength of light constant, and what we're going to do in terms of all our average this, manipulation that, is to work on the number of photons. We're going to leave the wavelength alone. Now, why that is, let me preview Wednesday's lecture. Why that is that we're going to think of the light bulb spectrum as being composed of a bunch of individual wavelengths. Each wavelength has a certain number of photons that satisfy the Boltzmann distribution. So our model, right, we're trying to model, don't ever forget, we're trying to model the spectrum of a light bulb. Whatever I come up with better be okay with this. If not, then I've definitely done something wrong. This has to work. Okay, so again, the spectrum of our light bulb, we're going to think of it as composed of a bunch of very closely spaced wavelengths. So we're going to keep this fixed. And that means that my Boltzmann handle, the thing I'm going to be like integrating and whatnot, it used to be velocity for Maxwell-Boltzmann. Now it's the number of photons when it comes to photons for our light bulb. All right, with that said, now what? Well, the first thing to do, okay, let's plug in our formula for energy. And that is E to the minus, I know we've got a bunch of E's now, and that's going to get worse next lecture, by the way. There's another E. Anyway, I'm getting ahead of myself. So that's NHC over lambda kBT. Kind of looks like what we had before. And here's our normalizer. Now that I've identified that N is our thing, I now know that I will be summing over all possible, my normalizer is going to be the sum of states for number of photons, and then it's really easy to identify what I'm summing. I could have no photons, or I could have an infinite number of photons, right? I don't have to like do any derivations to know that. Okay, and of course what's on bottom is the same as on top. It's just got that, it just has that summation. Okay, next step. Just like Maxwell-Boltzmann, I know it took me a long time to explain about how to turn this sum into an integral, and now I'm going to have to do it again, and it's going to take 10 minutes, but actually it won't. Okay, this weird thing happens. This weird thing happens when it comes to, when it comes to a Boltzmann equation, you always have to figure out the normalizer because, you know, dealing with this, like integrating this is not hard. I just used some software or I look up an identity. But this, like, I don't know what to do with this. Before I turned it into an integral of velocity and then it just turned into a bunch of constants. Here, actually this is easier than the Maxwell-Boltzmann deal because here's what I find online. I find an identity. An identity that doesn't require an integral, right? So that's better. Here's the identity. It is the sum of n equals 0 to infinity of a to the n, and that is equal to 1 over, I better actually look at my notes sometimes, 1 minus a. So that doesn't look so bad, right? It bothers me that that one was too long. Anyway, okay, so there we go. All right, now, as always, you just have to identify what's what with the identity and then apply it to your problem. Here it looks like A, of course, is hc over lambda kBt. Yeah, you know how we do this, I just lied to you. I know it looks like that, but really A is e to the minus, right? Because there's a minus there, there's not a minus there, so you have to take the minus. N is n, so you don't include that in A. A is separate from n. I know sometimes we can get kind of hung up on that, lambda over kBt. Okay, now the reason is that, you know, actually if this has got you a little stymied, here's an aside. I want to point out that e to some constant raised to the nth power is equal to e to the n times that constant, right? So that's what I'm doing here. E to the minus hc over lambda kBt to the nth power is exactly that. The summation results in 1 over 1 minus that. So this ends up being e to the minus nhc over 1 minus. No, that's not. Got to be careful here, right? This is 1 over something. That something is 1 over something, right? I know I shouldn't be speaking equations. I know that's got to be kind of annoying, but I just want to point out that this is e to the minus, this is the business end, this is the top part. And as much as I'm tempted to write 1 over this, it really, I've got a situation where I've got 1 over something. So really that goes out in front. Okay, so the normalizer ends up being 1 minus e to the minus b, right here. And I barely give myself enough room. There we go. Not, okay. So there you go. That is the Boltzmann. Let me double check that's right. Yeah, okay, I got it right. Got lucky. Okay, so here is the Boltzmann equation with the normalizer worked out. So cool. Now what? Now we have to use it, and we're going to calculate the average energy of a photon of a certain wavelength, and then Wednesday and Friday we'll take care of the fact that there's a light bulb. I'll preview a little bit about how that's going to work. I tend to do that a lot, but I think it's helpful. I hope it's helpful. Let's see, what do I want to do here? Tell you what, I backed myself into a corner. Let me take a break and wipe out the board, and we're going to do the next step to calculate the average energy, and it's a lot easier than Maxwell-Boltzmann, by the way, this part. It'll get a little harder on Wednesday. All right, I'll be right back. All righty, we're back. Actually, maybe we'll end a little early today. Okay, so this is our Boltzmann equation, which is normalized correctly, and of course, what do we want to do with this? We're going to figure out the average E, which is really a manipulation of the average number of photons. Regardless, you should know, of course, that the way that's going to work is we're going to sum over all possibilities, which is to say having no photons at this wavelength or an infinite number of photons. We then take the energy times the probability of having an energy. Of course, that's the definition of the average of anything. Of course, the probability is this guy up here. And what does that look like? That looks like, and I'll just write all this down again, being kind of redundant, but better than being confusing. Okay, so the energy is, of course, hc over lambda times n. And you know what? Let me write n up front. Right, n times number of photons times the energy of the photons. I'll show you why I changed that, the order I wrote that in. Anyway, in 1 second. Here's the normalizer. And my handwriting's not good today. I don't know why. It's kind of late, actually. I'm a little tired. Okay, there we go. All right. Now, the reason I wanted to arrange this the way I did is I want to point out that all of this is a bunch of constants, so as usual, we'll call it Q and toss it out. Notice that the normalizer here, you notice how n has been removed, the number of photons is not present, which is great, right? Because that's like the thing we're integrating on. Although, just like last time, to solve this, turns out like there's another identity. When I Google a little bit more, you know, you think like Maxwell-Boltzmann, now we've got some kind of integral, x e to the minus x times a or whatever. It turns out again that there's a identity that exists. Here, I better look this up before I just start writing. You know, sometimes I just start writing things down because I think I remember them, but I don't. It's n a to the n. And the reason this works, by the way, is because n is 0, 1, 2, 3, 4, 5. If n was 0, 0.1, 0.2, 0.3, this wouldn't work. But because n is an integer, you end up with these relatively easier to deal with identities, and you don't need to integrate anything. Okay, so there's the identity. As before, A is exactly what it was before. Just like A was always, I've got m over 2 pi kb, m over 2 kBt for Maxwell-Boltzmann. When it comes to photons, A is always e to the minus hc over lambda kBt every time. And you have some of these, you're going to have to do some of these on your homework. So anyway, okay, so what is this? Oh, here, I'll work this way. Q. Don't forget your constants. You know what? You know what? Actually, there's really no point in doing that. I shouldn't have even mentioned it. Yeah, you know why? Because it's actually, because you're not really integrating anything, this ends up being like stupid easy. So, you know, I'm just going to write all that stuff down. I shouldn't have even tried to, you know, there's no integration, so there's really no reason to remove all the constants out and try to simplify it just to bring them back in, because there's only one step to this. That was a little stupid of me. I shouldn't have mentioned that. Anyway, okay, so here's the constants, and now we use the identity, and I have A identified times e to the, and my handwriting is just awful today for some reason. There, I didn't like how that lambda looked. And then you got actually the same deal right here. And hopefully my handwriting isn't too terrible. And there you go. And that's it. That's it. Now, if I ask you this on an exam, stop. This is a reasonable answer, but of course we'll simplify it just because we've got 2 more lectures of doing more and more and more and more and more with this. Trust me, we've just barely scratched the surface. Okay, so simplify this, you may notice that this is basically that, and what you end up with is really quite simple. HC over lambda, business end, e to the minus HC over lambda, kBt, over 1 minus Oh yeah, same thing. Okay, last bit, and I believe this is also a very similar question on your homework. I'm going to have you do some more, I actually am going to have you simplify this expression on your homework, and I'll actually just kind of go ahead and I kind of tell you what the answer is, and I'm going to tell you what the answer is. I'm doing this because whenever I see these derivations like this, you'll often see this result, and then let me show you the simplified answer, and it's going to kind of bother you. What you get is hc over lambda. Problems like this are very common in physical science, so I'm constantly running into this. And every time I see this step done, I kind of do a double take. And so I want you to see that and know why it's happening. Okay. So we go from here to here. And you may be looking at that, and it's algebra. But what? I mean, how do you go from here to here? These look completely different. Oh, and why don't I have a minus sign? I must have messed up. Why don't I have a minus sign there? I'm not wrong. Okay, I know it looks like, as much as you should be able to do algebra, it looks like how in God's name did you go from here to here? Let me just go ahead and tell you. Multiply the top and bottom. Multiply the top and bottom by e to the hc over lambda kBt. And remember that e to the c times e to the minus c. Let me write that down. Okay, multiply top and bottom by that, and then you get this down here. And recall that e to the c times, I'm going to try not to say equations, because I know that's not really helpful. I can see it in my head, but anyway, so that's how you do it. Okay, I have 5 minutes left, which is just enough time, and maybe just a little bit early. Okay, so what? So what about this? So this of course, let's not forget what we just did. This is the average energy for a particular wavelength of light. And something curious is about to happen. Remember that our goal here is to describe the spectrum of a light bulb, which I've said several times now. Actually, kind of looks like a Maxwell-Boltzmann distribution, doesn't it? I should stop talking about Maxwell-Boltzmann distributions. We're not doing that anymore. But yeah, I have to admit that a light bulb spectrum looks a lot like the Maxwell-Boltzmann distributions we were just doing. And our goal is to describe this thing with our math, this and that. And I've got the energy of a photon. So you know what I can do is I can plug in of the x-axis is wavelength, and I can say, okay, this is 5,000 degrees. I can plug in 5,000 degrees. And when I plot the two together, what I get is something hideously different. Ta-da! Dark night. Anyway, this is not that. So what's wrong? Well, what's wrong is why we have to spend 2 more freaking hours doing derivations to figure out what's wrong. And the answer is this. Let me go ahead and preview. We're going to start on this next Wednesday. We're basically done with this. Just some more Boltzmann stuff, and I'll even have future questions with Boltzmann, this and that. But anyway, so what went wrong? What went wrong? Why is this not the answer? Okay, real simple. Okay, long wavelengths, like infrared light. Short wavelengths, like visible, and then these would be like UV and X-ray and whatnot. Now think about the light bulb. Now the light bulb is, how big is a light bulb? Probably about like 2 centimeters, let's always use SI. It's probably like 2 centimeters big. Out here, we have arbitrarily long wavelengths, wavelengths of like a meter, right? It's like radio. Radio waves are a meter. Your cell phones are actually millimeter. Anyway, these wavelengths go on and on and on. Why they could be bigger than the light bulb itself, right? So I think this wave fits in a light bulb quite well, But what about a really long wave, like a meter? Like, would a meter long wave fit inside of a light bulb? Of course not. So when you're out here, the problem with this average energy is it doesn't take into account that not any wavelength fits in the box. The wave has to fit in the box. And when you do that, you can't have these wavelengths. So that's why it gets crushed down to zero. So that explains this part of the curve. Now that's what we're going to describe mathematically in the next hour. It's quite obvious, right? I don't know, 2 centimeter light bulb, that's about right. Anyway, a 2 centimeter light bulb cannot be spitting out meter long wavelengths. That's just obvious, right? I don't think I have to prove that. And so that's why what we just derived is an error. The other bit, I had said this already, but the way we handle that is that we think of the spectrum as being composed of discrete wavelengths. And then what we're going to do is figure out whether those wavelengths fit inside the box. And again, that kills off the longer wavelength ones. But then let me go ahead and preview, because I have just another minute. While it's obvious that long wavelengths don't fit inside the box, there's another weird thing that occurs at shorter wavelengths, and actually we're going to cover that on Friday. It turns out that you may think of like, well, it either fits or it doesn't. So you either have a photon in the box or you don't. And that is fine for long wavelengths, but at short wavelengths, guess what? If the wavelength of the photon gets really short, then there's actually more than one way to fit inside of the light bulb. It's like a degeneracy. Think like hydrogen. You have a 1s orbital, you have a 2s orbital. But how many p orbitals do you have? You have 3 p orbitals. How many d orbitals do you have? You have 5. Those are degeneracies. You can have 3 p orbitals, you can have 5 d orbitals. So the same type of thing occurs as you go to higher energy, just like as you go to higher energy in a hydrogen atom. As you go to higher energy, shorter wavelengths, for light in the light bulb, you get degeneracies. You get more waves than can exist than you normally would have thought of, which is what we're going to cover here on Wednesday and Friday. So anyway, with that, say goodbye to the chickens, and I will see you all on Wednesday.
What do we say to the god of death?
Not today.